Start recording. Okay, everyone, hello and welcome to what is really, I guess, in some sense, the very first day of Handmade Hero programming, where we're actually going to be talking about programming the actual game. Because obviously we had to spend what I guess is about 25, I guess there's maybe a little more than that, but something like 26, 27 hours writing ourselves a prototyping layer that we could use on Win32, which we have mostly done. I mean, there's plenty of things that I would probably, if I was programming full time in my real life, I would clean up a ton of stuff, probably still in the prototyping layer, even though it is just a prototyping layer. But for the moment, it's plenty good for our purposes. And since I know we will be going back there and doing a real, serious pass on it later when we go to make a fully shippable Win32 layer, I figured I don't really want to belabor the point, cleaning up stuff in the platform layer at this point. Specifically the audio, obviously, it wants a couple more days of solid work to nail everything down, and also to kind of use on platforms where core audio exists and stuff like that, to use it, because the direct sound latency was pretty darn high, and I'd be interested to know if we could get a lower latency outputs, that sort of stuff. But for the most part, we've got a pretty solid prototyping layer that we can easily use to make the game. It's just not the kind of thing you would ever ship to end users because, again, it's for prototyping. So we haven't done the work necessary to make a really shippable Win32 platform layer, and we'll be looking at that in a bit. But for the next couple months, what we're going to be doing is actually making the game, which is kind of the most interesting part of the programming, I think, almost always, because playing around with platforms, sometimes it can be fun, but a lot of times it's just drudge work of trying to basically figure out exactly how to get something that is possible to happen on the platform, and you're kind of spending a lot of your time working around or experimenting with some stuff that some other programmer wrote who might not have been any good and isn't very well documented and blah, blah, blah. So that's a lot less satisfying. It's also it's harder for me too to sort of do these streams because these are educational streams. And when I am explaining something that we wrote entirely ourselves, I can do a much better job of explaining to you why everything works the way it does. Whereas obviously when we're doing a Win32 platform layer or a Linux platform layer or a Mac platform layer, I wasn't the guy who wrote the operating system. So when we get to a certain point, wherever that point is in, when we go down the levels of what's happening in, in the code, there's a certain point at which I have to just go, and we don't know. We call Windows, and this seems to be what it does, so that's what it does, right? And that's just kind of unsatisfying. So, I guess that's just a very long-winded way of saying, now we are finally getting to the point where we will know everything that happens because we have put ourselves in a position to basically write everything ourselves without having to now think about any platform in any way. And since we'll be doing the first version of the renderer in software ourselves as well, that means even rendering will not be hand-wavy because we will not be relying on anyone's driver or GPU to do the rendering for us. We'll be doing it ourselves, so we can literally know how every last little pixel got onto the screen, why it was there, why it looks like it does, how it was computed, where it came from, everything will be something that we can look at. And I'm much more excited about that because I think that's going to be really where the interesting stuff lies. I mean, platforms come and go, and there's a million platforms out there. There'll be a million more. And so really that's not that exciting of a part, but it's just something you kind of have to do. So with all of that, I guess I should do the standard preamble in case we do some code today. Welcome to Handmade Hero. We are on day 26 right now, which means we're about 26 hours into programming this game. I guess if it was a Monday that we started, we're on Thursday or something in the working week, something like that. If we were programming 7 hours a day or something like this. I don't know how much you guys program a day, but however much you program a day, you can figure out where in the week that is after 26 some odd hours. We are building an entire game from scratch, and we are building it from scratch for two reasons. One, because it's a lot of fun, actually, and I think as we now kind of get away from the Win32 side of things too, which, like I said, makes things definitely hairier. Now that we're in our own code, it's going to be a lot more fun because everything's under our control. But it's just kind of fun to have complete control of everything and to be able to do whatever you want. I feel is really very empowering. I kind of like that a lot. So I think it's a lot more fun, and also I think it's very educational. So one of the big reasons I want to do this, obviously this series, where we did everything from scratch was because I really want to be able to show how every little last thing works, because it's so interesting sometimes to find out how these things work. And a lot of times now, if you just use a prefab game engine or something like that, you don't really ever get to see all of the stuff that happens, and you don't get to learn about it all. So, I think it's really an important thing for everyone to do who's a game programmer to do once, to kind of do the whole pipeline once, so they can just kind of see it. It's super educational and cool, I think. So so I'm looking forward to it, and I hope you are too. If you pre-ordered the game on handmadehero.org, you should have gotten an email with a link that allows you to download the source code anytime you want. That source code zip has days in it. Each day corresponds to one of the days you see on the stream here. So we're on day 26, so you will want to unzip yesterday's source, day 25. Unzip that into a directory, and you will be in the exact same state that I am in right now. So if you want to follow along at home, that's the easiest way to do it, and you will be all set to go. Okay, so I have a bunch of things that I want to talk about tonight, and like I said, I don't know how much coding we'll get to. I said that I was talking about this in the pre-stream. I have a bunch of things that I want to explain because I think that game architecture is not very well understood by a lot of people, and I would also say that just architecture, software architecture in general, is really not understood that well by a lot of people, a lot of people in the programming world. And I think there's a lot of misconceptions. I think there are a lot of dogmas out there that can be very counterintuitive and also perhaps harmful to productivity, that yield a worse end product. And so I kind of just wanted to talk a little bit about software architecture, what it means, what the actual sensible things are there, and kind of then move from there into game architecture specifically and kind of how to think about it. Okay, so what I want you to think about for a second, if you will, is the term architecture. Because what's interesting about the term architecture is if you actually consider, am I in a painting mode here? There we go. There we go. If you actually consider what the term architecture comes from, right? It was something that comes obviously from building buildings. But if you think about the process, what happens when you build a building is an architect, right? The person who does architecture, they make a blueprint, right? They make designs for the building. They make a bunch of these blueprints. I don't know if you've ever seen them. They're all in a big roll. There's sometimes they're printed out by the hundreds for complex buildings, and like one blueprint will have like where the plumbing's supposed to go, and another blueprint will have things like how the floor is laid out or where the electricity goes. Who knows? They've got blueprints for all sorts of things. Well, the architects make these blueprints, right? Nowadays they make them on CAD things. And then what happens is, at some point, they hand these blueprinters off to like a contractor, right? There's a contractor, and they've got carpenters and stuff, and they actually build the building using materials, right? So the contractor actually builds the building, and building the building involves lots of stuff, right? Building in the building involves like nailing stuff in, right? Stuff together, right? It involves like, masonry. It involves cranes and hauling stuff around. So when people say architect, and they are talking about what we're doing in programming, it's kind of a little confusing to understand really what this means. And I think that it maybe puts up a few barriers to understanding, because one of the things that's true, if you take a look at this whole process in the world of construction, and we were trying to like use the metaphor directly, is that this right here pretty much tells you everything you need to know to build the building, for the most part. Like if I hand two different contractors the same set of blueprints, modulo like how much, how detail oriented they were when they're like nailing the stuff in, like, are there little gaps or something like this, how carefully they're doing their job. I'm subsequently going to get the same building out the other side, right? Like I'm not going to have a situation where like, one of the buildings was, sort of this long rectangular thing, and another one was like some kind of spherical omnidome when I handed off the same blueprint, right? And so if you think about that and what that entails, a lot of people who talk about software architecture take that metaphor kind of literally. Like if you think about things like UML diagrams, I don't know if you've ever seen these sort of things. Basically, there's a bunch of architecture, software architecture methodologies that really do try to reproduce this process. They try to make it so that when you are doing the work of software architecture, whatever that means, and we haven't really even defined what I think it means yet, but when you are doing what they think that word means, they essentially believe you are producing a thing which, when handed to people who literally do not have any knowledge about what you were trying to do with the architecture potentially, or how you wanted it done, would substantively build the same essential program out of it, right? So the blueprint is essentially the program, definition or spec, right? This is basically, the family of architecture that a lot of sort of like hardcore object-oriented style stuff goes, a lot of hardcore like pre-planning, diagramming, all that sort of stuff. That is how they look at it, right? Now, in my mind, I don't think that makes much sense at all, personally. The reason that I don't think that makes very much sense is because if you look at how this tends to play out in practice, really what ends up happening when you try to do things this way is that programs are so complicated and involve so many moving parts that if you could actually make a blueprint that actually does specify the program to a sufficient degree necessary to make it so there isn't any variability in what comes out the other end, then you have essentially just written the program. Like, these sorts of things, if you were to actually diagram them out to the level necessary, which some people actually do with these crazy tools, right? You would essentially have something that is more or less the program. Like a programming language sufficiently advanced could probably just spit out the actual end result from that process, right? And I feel like, and I could be wrong about this, but I feel like nowadays, certainly in game programming, but also I think the sentiment that I've heard from most of the people who watch Handmade Hero is they either explicitly or intuitively, and somewhat implicitly, have that feeling as well. Like if they've seen these sorts of things, they have had the experience that these do not tend to work very well, and that they cause basically a lot of upfront work that just doesn't pay off very much, right? And I feel very strongly about that because everything that I've ever seen that tries to go in that direction, where you have this sort of heavy upfront architecting of things, tends to fail at producing good quality programs in a reasonable amount of time, in my experience. They tend to take too long to produce too poor of a program. So, what I would actually propose is that this phrase architect or architecture, right, is actually kind of bad and misleading just to begin with. And if it were up to me, I don't think we would even ever use that phrase. So what I want to propose, oh dear, I don't know. I'm new to this drawing program, so let's see, fill with background color. There we go. So what I would like to propose is just briefly a way of sort of thinking about this. If you were in the same metaphor, I'd like to say where I actually think the act of software architecture comes in, basically. What I think it comes in is more like urban planner, honestly, right? Like, I think urban planner is actually the job that we're actually doing when we talk about software architecture. Architect, right? Whatever the architecture is, right? Wow, we're just having all kinds of. I don't even know how to erase that. We're having like spelling problems. All right, let's see. Do we have an eraser tool? Is there a way to erase things? I don't even know if there is. Help me, Krita. I should really practice with this program first. It's the only one that seemed to actually be working for us. So I assume that it's the one. Is that not selection? How do we select things? I don't even know. All right, fine. We'll just undo. There, you've made me do it, Krita. Okay, there we go. So if I have architect, wow, it's just like I can't draw today. All right, there we go. So if we have an urban planner, we have architects, we have contractors, right? I actually think of what people call software architecture as being up here. I think that this is like programming, right? this is design, right? And this is like the compiler, right? So basically, like the thing where things actually get built, that's the compiler. It's basically taking the blueprint, which is our code, and it's turning it into something you can actually use, right? So I say this is the compiler. It's not programmers taking a blueprint from a designer. This is actually what the compiler does. The architect job in real life, where you're making this blueprint, that's programming. And the reason that I think that's like actually what we do day to day when we sit down to program is because programs are very, very malleable, right? The reason that architects in the real world don't program, don't change their blueprints continuously as they build a building is because it's impossible to do so. It's much too costly. It's not because it's better, right? It's not because it's easier to have to pre-plan an entire building before you build it. If cost and time were no issue at all, you would much rather have the architect be able to just constantly fuss with the structure of the building through its entire production cycle, so they could build the lobby, see that the lobby was like oriented not quite right to the sun, so like change it and just move the lobby over to a new place so that it gets better sun, right? That's what they would love to be able to do that. But they can't, because building things in the real world is just costs too much money and takes too much time. So the act of pre-planning the architecture of a building is entirely because of real-world constraints. In programming, we have much more malleable structures of things. So the concept that we would want to do what they do and fix, sort of the blueprint ahead of time just doesn't hold water. We want our thing to always be malleable because we will be able to do a much better job. Just like an architect would be able to do a much better job designing their building if they had the ability to constantly mutate it, right? So I think that's actually what we're doing here. And I think we would apply the same principles during programming. Like I talk a lot about, compression-oriented programming, right? Where we sort of just splat things out and then we see how they take shape and then we sort of abstract them as necessary and rework things, all that sort of stuff. Very fluid. I think that's the same way you would build a building if you could, right? It just would result in buildings that were so much better than what we have today for the same basic amount of time. Because again, mutating code isn't really that difficult as long as you don't try to prematurely sort of factor it into pieces. So this is actually the part when we talk about architecture, and I feel like you're really more like an urban planner, right? You're really one level above blueprint. You're not talking about a specific building. You're talking about like how the city works in some sense, like zoning, this type of thing. How tall one building can be versus another because of various concerns, that sort of stuff. Why do I say that? I say that because if you look at how people normally talk about software architecture, when they just talk about, I'm going to architect this thing, I'm telling you about the architecture of this thing, what do they draw? They don't draw things that look anything like blueprints compared to code, right? They don't draw something that essentially sketches out the exact structure of the program as the CPU would execute it or anything like that. What they do is they draw these kind of diagrams. They'll do stuff like they'll draw something that looks like this, right? They'll say, oh, here's the Win32 part, and here's the engine, right? And here's, this is the game, and here's this library that we licensed or whatever, and it calls down to this, right? They draw what essentially look like street maps, right? I mean, that's what people do when they talk about architecture. They make diagrams that are very much about traffic flow and the rough relationship of things to each other and what their responsibilities are. That's it. That's what they really talk about when they're talking about architecture, right? And I think that's the natural intuitive thing to do, and I think it's the right thing to do. So when you're thinking about architecture in software, don't think about architect. Don't think about that in the real world, right? Don't think about that metaphor because it's wrong. When we talk about software architecture, unfortunately, we're talking actually about a completely different thing in the real world. We're talking about the high-level zoning and traffic strategy for our virtual city, right? We're talking about thinking through roughly where each thing has to be and what it should do and how much it's going to cost us and how efficient it's going to be for us to move things between them. That is really what we're talking about, right? And I feel like that's an important thing to kind of get straight, especially if you're a beginner, because a lot of times you're going to see people use this architecture term and they're using it to talk about many different things that aren't all the same, and some of them are good things to pay attention to, some of them are actually very deleterious and you should avoid. And so I just want to kind of frame it a little bit differently than it's typically framed as we go into this, so that it's a little clearer in people's heads who maybe aren't familiar with some of these processes. Okay. So, what are we trying to do? I'm now going to go ahead and get a little more specific. We're in metaphor land here, and I only wanted to do that because people are often talking in these metaphors, and I kind of wanted to confront those up front. But from now on, we don't really need much in the way of metaphors because I can talk about actual specifics now that you know that what we're trying to do. So basically, in software architecture, just architecture in general, you are trying to come up with strategies for doing what essentially amounts to separation of code, right? And there's a number of reasons that we do this, but basically separation or boundaries, right? Basically, depending on how you want to think of this. This is mostly what we're doing when we're talking about code. And again, it fits with the urban planning thing very concisely. It's about drawing that property map that says, here's where everything's going to live. They don't overlap. Here's the traffic patterns that connect them, right? And here is what each thing is supposed to be about. You know, what does this section of our city do? You know, that sort of thing. Architecture is mostly about defining these. And the reason that you want to define them are usually for either reuse, right? That's a big one, because I want to be able to have components that are easy to reuse, for example. So maybe I want to separate my code in a way that, for example, on Handmade Hero, with our Win32 prototyping layer, right now it really doesn't know very much about the game whatsoever. So if we wanted to turn that into a reusable platform layer, it wouldn't take very much work because we've done a good job separating it out from what's going to be the game. So if you think about that, that is a compelling reason to draw separation, you know, to put hard separation into large chunks of your code, because then you can take those and reuse them and don't have to write them again. That's one reason, right? Another reason is division of labor, right? So basically, if I think about, you know, trying to write this code, Handmade Hero, I'm writing it all by myself. So that's, you know, not really a problem. But let's say I had 2, 3, 4 programmers on this team, or, you know, worst case, you've got some like project that's like an operating system project that's got 500 people on it or something. Well, we need to kind of have different people working on different stuff so that the communication requirements between them doesn't overwhelm the entire project, right? If each of us is all working on whatever code we want anytime we want, when things start to get scale up in the number of programmers, that becomes prohibitively expensive because we would constantly not know what each person is doing and we'd constantly work at cross purposes. So division of labor is another reason that software architecture typically comes into place. Another one is simply like mental clarity, right? And it's weird to list that one, but it really is a sort of important part of things, which is that when you tackle very large programs, and this actually is true regardless of how many people you have, whether there's a division of labor or not, when you tackle very large programs, there is a challenge to most people, most programmers, in keeping the entire thing in your head. As you get up to larger and larger programs and larger complexities, sometimes your architecture is more about keeping things separate so you don't have to consider them at once. And the reason I say that is because if you imagine that there was no separation between anything in the code and every last little thing has a bearing on something else and how it works, if that is constantly in flux, then any change I make to my program has consequences for the rest of the program. And that is essentially, you could think of it as an n squared. We haven't talked about this yet, but for those of you who know what that is, you could think of this as an n squared problem for your brain. Your brain, every time it makes a change, has to go consider all other possible parts in the code. And so for every, for the total number of changes that you have to do for the project, each piece of code that you make a change to essentially affects all the other pieces of code. So if the pieces of code were numbered n, then each, if you have to do a change to however many, I guess it's n squared, but it's really, I guess you might even say it's worse than n squared, because if n is the number of pieces of code and m is the number of changes, which is often actually higher than n, so it's really actually worse than n squared, but it's at least n squared, because the number of changes times the number of pieces of code is what you end up with as you get towards the end of the project is crazy complicated, right? Every time you make a change, you have to consider every piece of code in the system and how it might affect it. So sometimes we do that kind of separation, not because there's any actual practical reason, but rather just because doing anything less would be simply too much brain power to make progress, and either you will spend too much time thinking about each individual change and that will slow your rate down, or you'll just make mistakes because you forget to consider certain pieces of the code that are depending on the thing that you're changing. Okay. So this is typically why, right? This is why we do software architecture, right? And then we also have other things to think about here, which, if that's the why, this is sort of the how, which is things we want to accomplish, or I shouldn't say how. It's not really how. This is sort of like our goals, I guess you might say, in terms of like when we are doing these things, right? When we are trying to accomplish these things. Even goals is a bad word. I don't know what I'm going to call this. I'm going to list them out first, and then maybe we can think of what the word is, because I'm not sure what the word is that quite encompasses what I'm talking about. But basically, I guess, well, you know what we could say? We could maybe say there are some metrics. There are some things we could measure, right? There are some measurements that we're trying to think about as we're doing this that have some bearing on when we do these sorts of separations. And typically, these are things like sort of temporal coupling, for example, right? Like when I am making, and you can think of this is sort of like thinking about the quality of our little city that we're building here. One thing we could think about when we're actually doing this thing and we're kind of starting to break up stuff into pieces, we have a bunch of different things that we need to think about between those pieces. So temporal coupling is like I have two pieces that I've sort of separated. I've drawn boundaries between them. When they occur, and I mean literally the time at which they can occur in the program, that may not be arbitrary. An example would be, let's say I have a physics system and I've drawn a boundary around that, right? I've said this is one component, so I've separated it out, right? And I have a renderer, right? And I've separated that out. Oops, renderer, right? So this is responsible for drawing the game, you know, and this is responsible for moving the things in the game, okay? Well, if that's the case, then obviously I can't just run these two things completely randomly. There's some kind of a temporal coupling between these two that says something along the lines of, this has to produce data, right, that this can read, or something, right? Because if this is what's moving things and this has to render them, then we know that we can't render the stuff for a frame until the physics has computed what that thing has done for the frame, right? So there's often temporal coupling in there. Similarly, there's like layout coupling as well, right? Like basically if this has to spit out stuff that this can read, well then there's a directional coupling this way that basically says, okay, whatever data this thing spits out, this thing is now dependent on that format of the data, and that could have implications for performance. Maybe this thing wanted it in a different way, and this thing wants it in a different way, and now we have to figure out, do we translate between the two ways, or does we try to make one work with the other one's way, and blah, 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 right? So we can have a coupling like in the layout of things, right? We can also, you know, have some other metrics up here, right? Which is sort of just the, I don't know what you want to call it. We could call it sort of an ideological coupling, right? Which is to say that we may, especially when it comes down to this reuse thing, we may have some things to think about that are just about what is sort of the way in general that these things work, and does that have a bearing on where we could possibly use them? Some examples of that would be like, is this thing multi-threaded? Does it have to work with a job system? That sort of thing. There may be stuff that's just how you wrote the code in general, internal to this, has sort of a bearing on what sorts of systems it can slot into, just at its basis. Another one would be, so the examples there would be like threading, memory, like what kind of way does it look at memory? How does it use that? Width of computation. So like, is it SIMD? Does it use SSE? These sorts of things. Can it? Those sorts of things. When we write things, we've got a bunch of things that sort of have that may tie code down to a particular way of working that we need to be aware of, right? So we have lots of stuff to think about here, and this is by no means exhaustive, but it's just an example of the sorts of stuff that we're thinking about when we go to actually do sort of the software architecture, if you will. Now, there's one more that I'm going to put on here, which is not a coupling thing, and this is the metrics. But this is basically like, I'm going to just say fluidity, right? Fluidity is very abstract and difficult to measure. It's one of those things where you know it when you see it, but it's pretty hard to say like what you would measure exactly or how you could really say ahead of time what would or would not be fluid. But what I mean by that is there are architectures that may do very well by all of the metrics that you might look at here, like in terms of coupling and they perform well, they're efficient, they were written well internally, that sort of thing. So everything about them's good. There's nothing, the architecture is not doing anything wrong in terms of providing these things in terms of setting the stage for the particular parts that it then have to get implemented inside that architecture. It's done a good job setting the stage for it to all be successful, and it can be written very successfully, and you're done, right? But it might be very fragile, or I should say perhaps too sort of stuck in the way that it's designed, such that if for some reason some of those architecture decisions turn out to be wrong, changing them becomes disastrously difficult, right? It could be that you've made it such that everything has to work the way the architecture was designed, and any change to it, everything comes crashing down. Then there may be other architectures which, maybe don't score quite as highly on some of the other things you might measure, but they may have a great deal of fluidity in them, where they can basically handle like, oh, we got kind of partway through it and turned out this was a bad idea, and so we, could rework it very quickly, that sort of thing. That can be very, very valuable on projects, especially if you're not sure what the architecture should be. And the first time you do any type of system, you're probably not sure what the architecture is going to be. And so that fluidity, much like with, when I say the sort of the semantic, the compression-oriented programming, right? Having the ability to constantly rework things quickly in your architecture is very valuable as well if you can get it. Now, sometimes because you're talking about such big pieces, that may not be easy to do. That may be very difficult. And so it's by no means necessarily true that a architecture that isn't fluid anymore is bad. It may be just that you've gotten to the point of complexity where fluidity is just not possible anymore. And so, again, one of the things you try to do, much like with the semantic programming approach, is you try not to lock things down in the architecture any earlier than you have to until you've sort of tried some things and seen that they work, at least in one case, before you sort of make steps in those directions, specifically for the same exact reason you don't do it when you're talking about just regular ordinary code, right? So, with that in mind, let's talk about a few specific sorts of things here. I think that's a good enough sort of a good quick background on software architecture and what's sort of going on there. So I'm going to talk about the actual game architecture now and sort of how all that applies. All right, so game architecture. You now know one part of how I think game architecture should go. And again, like architecture is one of those things that you kind of build up over time techniques on how you like to architect things, much like how you build up over time techniques on how you like to write code at the lower levels. So what I wanted to kind of talk about is how the sort of game architecture process works And one thing that you've already seen, though, is you've kind of seen me cheat a little bit, and this is because I don't even know how to not do the cheating anymore. But basically, I already know what I think is a good architecture for a prototyping layer and a platform layer, both. So, we have down at the very bottom of everything, right? We've got Win32, and we've got, OpenGL or Direct3D, these sorts of things, right? Oops, Direct3D. So we basically have some stuff underneath us that we can't do anything about. It's there and it's designed the way it's designed, right? And I already showed you how to basically make, there's a platform layer here, right? And I already showed you basically how I think that thing should be designed. Now, we didn't code a proper platform layer because, like I said, we only did the prototype version. We'll do the more proper version down the line. But the architecture, the way it's structured, is roughly what I would normally do. This platform layer talks to Win32 and talks to whatever the graphics library is eventually. Right now, we are fortunate in that we don't actually have to really do that because we're just pushing a bitmap, so we're kind of just doing it through the Win32 API. But eventually, we'll have to deal with that because we're going to need to use one of these guys for hardware acceleration. So eventually, this will be there. But we wrote this code, and we basically had two ports in it. There's game update and render was was game. Game update and render. Let's say GUAR. Game update and render, right? We have game update and render, and we have get sound samples, right? Those were the two things really where data is flowing back and forth. And you might actually, I don't know how you, I never find these diagrams to be all that necessary to be specific. I'm just going to point to them to talk about parts. So I don't even care which direction these arrows are going. But one way we might say is that it actually looks like this, right? Because really game update and render, these things go back to the game, right? And get sound samples, right? So basically these things call into the game. But really with no loss of resolution here, this is essentially what we've already done, right? We have the operating system. This was written by Microsoft, right? We have this platform layer, which we wrote the prototype of, and we wrote that for the first 25 hours, right? That's what we did. And now we're going to talk about doing this part right here, right? So the reason I said that I cheated is because I didn't have to go through the learning steps on this stream, rather, of how to design a good platform layer. I just already know how to do it because I've done it probably something like 15 times. I don't know. I've written a lot of platform layers in my day. So I pretty much know what makes me happy about a platform layer, and I pretty much know exactly how I want it to look. So when I sit down to write a new one, it's really kind of just a rote process at this point. I just know what it should look like and what it should do, and it's just a question of me fussing with the OS to get it to do it. That's it, right? So I really couldn't show you anything about the architecture process in here because it was just a given. And I couldn't even really, there's be no way for me to really pretend that I didn't already have a goal in mind, because I do, right? With the game, we're going to be much more fortunate in that respect because I have no idea how to architect this game. I mean, that's not entirely true because since I've written game code before and game system code specifically, I do have experience architecting games. But every game's architecture is usually a bit different depending on sort of what genre the game is, what sorts of stuff it needs to do. And so I don't know a priori exactly how this game's architecture should look. So over the next several months as we build the game, I will be going through the same sorts of steps that I normally go through to improve and refine on architectures, specifically as sort of like part of the core goal of the stream is to show that kind of stuff. So we will actually be doing a lot more talking about that as we go. So the only thing that I really want to talk about tonight in our last 20 minutes is sort of what are some of the principles of game architecture, things that I have learned and that I kind of think are true from past experience, to sort of set us up for as we start to go through and do this kind of programming. What are we looking at? What are we trying by default first? What are some of the techniques that we're going to use? That sort of stuff. So I'm just going to talk about that a little bit. Okay. So inside the game, oops, What is the hotkey for fill with background color? Backspace. There we go. All right. So let's talk about that big old block that just said game on it, right? That big old block that we had. We're now inside that block, right? Well, so one thing that I talked about originally, or that I did, I should say, is game, update, and render, right? That's one of our entry points, right? In fact, I'm just going to keep using Guar from now on, I think. So we kind of know, right? I'm going to invert this from the diagram before so we can have kind of a downward flow of things here. Maybe, you know what? Maybe we do it from the side. I don't know. So we're going to get a game update and render call from the app, right? So we basically now know that our game update, our game architecture is based around getting a call that says, you know, here's a T for how much time basically has elapsed. How much time do we need to advance things by? So we basically need to do a T update to advance the state of the game, right? We need to do a rendering, so we need to render to the bitmap that it gives us, right? That sort of stuff. And implicit in this here, in this T update advance, is that we have to process the user input that it passed us, right? Because it's going to pass us the keyboard control and the gamepad control, right? That's what's going to happen here in that sort of advance thing. We're going to render to the bitmap, and then when we get we don't even have to really think of this as a separate call. We have to be able to handle it as a separate call. But the get sound samples stuff really is just an extension of this. If I would have preferred it, and in fact we had it this way originally, if I felt like we could get away with it, and maybe we will eventually, depending on how we go, I would actually have this be right here. I'd actually have output sound samples actually be something that just happens as part of the game update and render call and not have a separate call. So really, I like to think of the game as getting a single sort of point in time where it goes, okay, now's the time to do all your work from the platform layer, and there's nothing else that's going to go on here, right? So let's talk about these things because I think they're basically endemic to all games, and I'm going to well, I guess I'll keep them separate for now. I was going to say AV output can kind of usually be lumped together because they're very similar processes. Sound is usually basically a subset of the complexity of graphical rendering. But so what actually has to go on in these things, and what is our game architecture going to be concerned about? So I'll just state some pretty straightforward stuff right off the bat. So regardless of how much multi-threading we do or anything else we might do, right, we know that essentially if our game loop has user input in it, we want to process the user input first, we want to update the state of the world, and we want to render, right? Now, the user input, we always want to process as close to the updating as possible to reduce input lag, right? You could imagine us processing the input, like we could update the world, render the game, right? Not do this at the outset, and then take a look at the input and process it here. If we did that, we would essentially be introducing a frame of lag, right? Because we did an update even without considering input that we actually had at the time. So definitely what we want to do, right, is we always want to basically say, okay, input gets integrated in the update right away, right? We don't want to hold it over. So we know that basically this update, whatever we do to update the world, we're going to have to take into account the input right there. So the question is, right, or I shouldn't say the question is, but basically we know that if we look at our sequence of operations, we know that the very first thing we're going to have to do is look at that user input, right? And then the next thing that we're going to do is something else, right? And we don't know exactly what it's going to be, but we know that we want this to be as close to the head end as possible, right? So let's talk about update and render. A lot of games will do something where they have like update, right? And that's something that they do, a step. And then they actually have another step that's like render. So rendering and updating are totally separate, right? I can appreciate that from a ideological standpoint, certainly. Saying that I want to be able to update the game separately from rendering it makes sense in terms of a desired set of operations. I might want to update the game, I might want to render the game, maybe I don't want to do one or the other, maybe I want to do both, that sort of thing. Maybe I want to update the game 2 times and then only render it once, blah, 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 blah. So if you think about what this means, you may write the code the way I just said, where you've got an update step that you call separately, right? And a render step that you call separately, and these are different functions. So essentially, when we start to think about the things I was talking about in the architecture, you're drawing one of those boundaries. You're drawing a boundary between update and render. I never draw that boundary if I can help it. And here's why. If you think about the way modern computers work a lot of the times, is they have a very high penalty for missing the cache, right? A CPU really likes to be able to do things in its cache, right? A CPU has some amount of cache, however much it is. It pulls things into that cache when it's working on them, and while they are in that cache, if they do not get evicted, as long as you can process stuff within that cache, you get massively faster. You know, you're talking 10, 20 times faster, sometimes more. Because the time it takes to go out and get stuff from memory is very long, so unless you can accurately predict exactly what memory you're going to need quite a bit before you need it, there's not a lot you can do to work around those kinds of problems. Since that is true, I usually find that it is not a good idea to say that as an architectural decision, your updating and rendering are split. Take for a very simple example, let's say I have some kind of fancy particle system in my game. And so there's 16,000 particles. And I have to loop through all 16,000 particles, and I need to do some kind of physics update on them. And then I need to produce some stuff in a vertex buffer that's going to get sent to a graphics card to render them, right? Well, if I actually loop over all of those things twice, once in the update to update where they are, and then once in the renderer to render them, at the very least, position and probably velocity, probably potentially also color, are getting pulled into the cache and evicted from the cache 2 times, right? They're getting done on the update pass and on the render pass. So it would be much more efficient if we just did it in one pass to produce both things, right? And so I do not like to draw that boundary. For some things, it's fine to have that boundary happen, but at the game architecture level, I never draw that boundary. I don't like to put it there. I like to have update render basically be one coherent step, right, that happens together, if that makes sense. So this is actually what I do. I do not ever do, something that looks like this. I never do that if I can avoid it, because basically I feel like this is a much saner way to go in terms of when you need to actually start optimizing for performance, acknowledging the fact that there are many types of things that want to get updated and rendered together. And render is kind of a difficult term here, because render in the final version of the game is not really about rendering. It's about stuffing things in buffers that eventually go off to a GPU. But you know what I mean. So sort of this term render, think of that more as render prep, because nobody actually does rendering anymore. And in our case, we won't really be doing that either. It's input, update, render, and then GPU or whatever is doing its thing. We will also have that step, right? Only in our case, we will be implementing the actual code that, and on the CPU, so it won't be on a GPU, right? So really there's that final step. So when I say render, I just want to make it clear what I'm talking about. I'm talking about the thing that prepares all of the buffers for the graphics subsystem to handle, which is normally on a GPU, but in our case, for the first couple months, it's going to be our own renderer. Okay. So, this runs sort of in parallel with another part of the game architecture, right? So we have our input that's got to come in and be integrated first. That may be integrated directly into this, but I think actually probably most of the time it won't be. I think it'll be a separate step that happens here, just because there's not a lot to do with input processing. It's not a performance critical thing usually. You're just setting some state that then gets used by the update later. So this will probably be a separate part that's just like the player control code that, that executes something like that. You do the update and render. And then basically we do now know that architecturally speaking, we're going to get some other call down here that's a separate list of things that have to happen, which is, sound output, right? And so these things have to pull from somewhere. So what I want to talk about now is where these things pull from, basically. I really wish I knew how to erase stuff in a diagram. I realize that may be too much to ask here. Let's take a look. Nope, that's not it. Let's try again. There we go. Can I select, deselect stuff? Is that on the table? Select. Control-Shift-A. Control-Shift-A. There we go. Oops. There we go. All right. So basically, I'm saying that our architecture would draw boundaries roughly like this, right? We have to draw this boundary because the platform layer drew it for us. We have to draw this boundary because this is, I'm sorry, we don't have to draw this boundary, but I'm saying I probably will. So there's another boundary that we have that is kind of a parallel style boundary. And what I want you to think about is basically where this stuff is getting its data from, right? So there's one form of game architecture, which is sort of the loading screen architecture, I would call it. Okay, the loading screen architecture is the one where you have some event, which is your change level or something event, and you go into some kind of a loading screen. And the loading screen then goes through all of the assets that it thinks it's going to need for whatever it is that it's doing, whatever it's about to do, like whatever game level you're about to play, that sort of thing. And the user gets to sit there and watch a little spinning thing and a quote from one of the characters in the game or something like this, or a pro tip like press reload quickly to reload quicker or something like that. During that time, what happens is the resources for the game are being loaded from somewhere, right? So resources are coming in. Usually they're coming in off of a disk of some kind. Oftentimes it's optical if you're on a console, but then it's like HD or SD drive if you're on a PC, right? These things are coming in. Sometimes they can even come over a network. I'm getting a little close to my head there. I don't know if I can. There we go. So essentially what happens is at some point you've got to get these resources out because steps here depend on it. At least this step does, right? And possibly this step too, depending on how we choose to do our sound output, whether it's buffered. But if we decide to do a way where the output just does a quick thing, there would be a 3 in here, which is sound prep, right? Where it prepares the output for what this will get handed back. So either way, somebody, sound-wise, is pulling off of these resources. So basically we have AV resources here, right, at the very least. Now we may have other things. This is a procedural game, so we probably won't. But so in addition to AV, you may have D as well. Audio, video, and just data, right, like gameplay. We could call it G, like level structures, that sort of stuff. That can be in there too, right? So we've got these resources. We may call them S, structural resources. I don't know, because they could be structural for audio and video as well. Like here's a graph of different meshes that have to get loaded. Who knows? So this resource part is also an architectural part, and I'll kind of sort of explain why. In the loading screen style of doing things, there really is no architecture concern as far as the loading part goes. I mean, there is a little bit, but not very much. The reason is because essentially you're not talking about one integrated system. You're talking about two systems that run completely separately, so there isn't much of an architecture concern. When you have to load, you load, and none of this stuff is happening, right? And when you are done loading, you do this, and then you never load in here, right? So the full-on loading screen mentality is one where you basically don't really have to think too hard about how this architecture is going to work. But there's another way of doing this, which is the streaming mentality, right? So if I go ahead and say, let's not do that, oops, never going to get used to that. Let's say we don't want to do that. So what we want to do is we want to do streaming. Now what streaming is something where we say, okay, I don't want the user to have to sit through a loading screen. And I want to be able to maybe have very large worlds as well, so I don't want them to have to hit parts in the world where they have to stop and it loads Like, I don't know, the old Half-Life kind of, you walk around a corner and you go, and it's got to load, whatever. I don't want to, have any of that. I want the game to just boot and run, and it always just goes and gets the resources that it needs kind of in the background using, because there's obviously lots of resources now for doing that sort of thing on the computer. There's a lot more firepower that you have in terms of being able to run things concurrently. So assuming that that's the case, you want to make one of these streaming things, you do now have another architectural boundary that you have to draw here, right? You've got an architectural boundary where there's essentially a two-way communication. There's this side of things has to be able to tell this side of things what it needs. And then when those things are ready, there has to be a way to communicate back so that it can actually know that they're there and can use them, right? Now, this is a fuzzy back and forth because what you choose to do there affects how you might think of those arrows. But this is basically, the situation. You've got a kind of bi-directional linkage that goes with these sorts of things. This is going to be a very, very important part of our architecture to think about as well, because a lot of people do this very poorly, this part. And it's also where, I know a lot of people have asked about IMGUI, right? Immediate Mode Graphical User Interface. Well, IMGUI is really just a special case of IM design. Like, you can design any architecture to be IM or RM, basically. IM is immediate mode, for those of you who don't know. And RM is retained mode. Okay? Immediate mode is a way of describing an API boundary where the calling side does not have to remember handles to the target side. So the classic example here would be like in a rendering API, where these terms first came from, to the best of my knowledge, are IM and RM. If I have to call you to set up like a scene graph, I say like create a node in my scene and it's got this transform and give it this mesh, and then create another node that's a child of that mesh, and I create this like scene graph, and then I say render, right, at the end, and the library is responsible for doing all that traversal and rendering a scene graph. That's an example of retained mode, because basically the retain is talking about what happens on the other side of the boundary. It's retaining all this structure, basically, that you have. I shouldn't even say it that way. So I want to just slightly finish this, but we're going to talk about this in a lot more detail on future streams, so I won't belabor the point. The term retained mode and immediate mode are actually bad. I mean, I'll say that up front, because this retained part is actually not important. It's the API part that's important, and I will be showing you this in very explicit detail later on when we actually do some of these systems. But basically, the way to think about this is probably not to quite think about it the way I just said, unfortunately. The way to think about it is actually about lifetimes, right? And I was trying to explain it the way that these things originally worked in renderers, which would have been true for the way I was saying it, but I'm not going to use them that way because it's kind of weak sauce. So we'll have to wait till we actually get there. But the right way to think about these things is actually lifetimes. So in immediate mode, the calling side is unaware of the lifetime of anything in the system. They just don't know, right? They are unaware of how long something exists. But in a retained mode, they are. So again, the example would be in that scene node architecture, or anything else really. You could even imagine, in fact, we could do a pretty good example with, say, OpenGL or Direct3D. If I have to create a texture binding, right? I have to say, I want to create a texture binding. Please give me a handle to a texture, and later on, I'll tell you when I need to release that texture. That's definitely retained mode, right? Because I have to mirror across the boundary this notion of this object's lifetime. The application that's calling Direct3D or OpenGL is aware of and manages the lifetime of that thing, and that's retained mode. Immediate mode are like, so those parts of like OpenGL and Direct3D are retained mode. Immediate mode is when I don't have to care. So for example, let's say I do something like in the old fixed function pipeline, where in OpenGL Direct3D I would say, I want to set this blending mode, right? I would say, here's what the blending mode is. Well, when I set that blending mode, I don't have to care how long that's true for, right? I just know that I set this blending mode and I do some operations, and the operations that are done will have that blending mode. Later on, someone else will change the blend mode to something when they want to do a different operation, but I don't have to actually undo that blend mode set. I don't have to like destroy the blend mode after I'm done with it or anything like this. I just say I need it and it's there, and later on someone else says they need something else and it's there. That's like immediate mode. These things have a lot of consequences. Your choices of which of those two things you pick at any point in any one of the layer boundaries is definitely going to be crucially important to how well the system functions, because there's tons of trade-offs that occur for each one of the decisions that you make. So we will be harping on this a lot. We'll be harping a lot on it here. We'll be harping a lot on it in here as well. And so that will get a little more in detail. All right, I think we're out of time. I saw the timer pop up there. The timer, like I said, does not lie. So I believe we are now officially out of time. So I will finish, I will say that that is all we're going to talk about architecture-wise today. Hopefully you've got a reasonable idea of what I'm talking about now when I talk about architecture things. So really, the next thing that we have to talk about is sort of how we're going to structure these sorts of things. And that will again be something that we can actually start doing code. So tomorrow we should be able to actually start doing coding on these things, because this is, like I said, I don't really like to do architecture at like a super high level pre-planning sort of a thing. I like to sort of do it more organically like I do the rest of my code structuring. So that's okay. But I felt like it was important to kind of give this general overview of how we're thinking about things, just so we can sort of have a little bit of opinion on it. So tomorrow I'll start off by redrawing this diagram basically in a little more detail of just how we're going to try to approach things. And then we'll sort of dive into doing code on this sort of stuff. All right, that brings us to question time. Please, if you could, keep your questions to things that we covered in today's stream or in previous streams, and put C Muratori in the questions so that I can see it, because I've got a little thing that basically says, you know, that filters questions for me based on whether or not my name is in them. So I won't see it if you don't. Okay, let's see. Let us see. Questions. Does anybody have them? If there's no questions, we all go home early tonight. Remember, it's not Handmade Hero with the @ it's C Muratori. Handmade Hero I won't see. Although, you know what? I should just start scanning for that as well. I suppose I should. I'm going to make a note of that. All right. Is immediate mode retain mode like IOC dependency injection? Inversion of control dependency injection? I'm afraid I'm not familiar with those terms. So I could not tell you. The one qualm I still have with the fixed time step style update render we're using is that I don't understand how it reacts to missing its target frame rate. What if the end user machine is slow enough that we miss 30, 60, or 30 FPS? Can we build in safeguards about that? So no. Basically, if you can't run at 30 frames a second, you shouldn't be running a game. Because anything less than 30 frames a second will look choppy. So you shouldn't do that, ever. Never write a game that runs at less than 30 frames a second unless you are intentionally doing some kind of strategy game that just doesn't care, I guess. And the way I would say that was if we were going to plan on running at sub 30, we would at the very least still run the game at 30. We'd have the renderer in like a separate thread or something that would update the graphical bitmap only every other frame or something like that. But you never, ever, 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 ever want to actually run the input at less than 30 for sure. But I would argue you never want to run the graphics at less than 30 either. What I would point out, though, is we're not architecting the game around a fixed time step. The time step will take the T. So our game can actually run at any frame rate. just to be clear, the game architecture runs at any frame rate, because if you're going to pass in a t to update the game with. So you would be able to run the game at 15 frames a second, just don't, if that makes sense. And if it's graphical quality that is causing you to not hit 30, what you want to do is you want to scale back the graphics so that you do hit 30, if that makes sense. Are you going to work with virtual file systems to store data resources? Well, I mean, sort of. The phrase virtual file system is really a little bit of a pet peeve of mine. Like, almost no games ship with virtual file systems. A file system is a very specific thing that has a bunch of capabilities. Usually what people do is they just essentially have a zip file. They have like a pack, like where they pack things end to end. That's not really a file system. I understand your argument for blending update and render for particles. In general, don't you want many things to update before rendering, though? For example, if we update and render the player, only to later update the bullet and find it hits the player's reaction animation is a frame off. So I think I would caution against thinking about updating in that way, because you've basically baked into that question the assumption that the way that you update things like bullets and players is that you loop through a set of entities and whoever happens to be first in the list gets updated first or something. That's usually not a very good way to write your update loop. I realize that is the way a lot of games write their update loop, but I would never do it that way. So when we get to sort of how we write those things, I'll show you how to structure things so that we update things correctly. Because the other way to, I would point out that in that situation you talked about, you actually have another bug, which is that what if you were to, what if you were to update the player, right? And then you update the bullet, and you find out that the thing that had happened with the bullet should imply that the player couldn't have moved to where they were going to move. Like the bullet hits a button that opens a door, and the player hit the door when they were updated. So at that point, when the player would have been going through the door, they actually stopped, which is a bug, right? So you can't just think about things even in terms of update and render. You have update dependencies in general, and update dependencies have to be handled. It usually has nothing to do with rendering or not. So if you have things that are dependent on their order of resolution and you care, those have to be baked into the update understanding itself. And it really doesn't have much to do with rendering, and you could leave rendering out of it entirely and you still have that problem. How strong is the notion that you perform the update and render steps together? What about a situation where update order requirements differ from render order requirements? Well, so the idea is not that it's a strong division. The idea is, that it's a strong blending. The idea is that architecturally you don't make the distinction. So you don't want to pre-say a priori that update and render can't happen together. And so that way anything who can be updated and rendered correctly together will be, and anything that can't won't be, right? But there's a great many things that can be, and so not making an architectural division there helps you increase performance. Let's see. Okay, so Jonathan Blow is asking to explain the variable in this session. And one of the things that I didn't talk about when we talked about game architecture, obviously, was where the variable fits into all of this. The reason that I didn't do that is because still, I mean, I've been programming games for like 30 years now, I guess. I mean, I was little when I started, so I don't know, 20 years professionally. I have never actually seen a game engine successfully create a variable for more than a fraction of a second. So we really just have not been able to study these variables, if they even really exist. I mean, we only see them indirectly, right? So again, Jonathan, it's a good question, obviously, but I feel like it's impossible to really explain. It's like a frontier of computer science. How do you handle update versus render for a game that can run at 60 or 120 FPS depending on the user's display? Well, it doesn't really matter. I guess there's some, if you are concerned about wanting the game to always run at the same time step, even if the rendering is happening at a different time step, then that's a sort of separate question. But assuming you just mean 60 or 120 FPS, it's just this t variable, right? Either the t variable comes in as 1 over 60 as the amount to update, or 1 over 120. That's the only difference between the two scenarios you just described. So you don't really have to change anything. When you say you like to do update render together, are you implying that you do it on a per object entity basis? No, you do it at whatever granularity makes sense for the system. So like for particle systems, for example, you would do it for the particle system at once. For objects, there may be a dependency graph that has to get traversed for the update. You never know. So it's about not drawing an architectural distinction so that every portion of the update code can choose to have the rendering bound in or happen later, depending on which one it wants. Are we planning on networking with the game loop? Well, we may do networking as a separate stream someday after the game is done. But no, we're not going to do networking because networking is a whole separate topic that I don't feel like we'll really have time to do within any reasonable sort of size of this stream. How are you going to handle shaders in Handmade Hero? Well, we will cover shaders when we get to shaders. Let's see. What language are you using primarily? Is there somewhere we can review these streams? We are using C with a little bit of C++. And yes, if you go to handmadehero.org, you can go to a number of places. There's a video archive, which is the direct YouTube archive for all the things. And you can also go to this news and forums link, which has for some, it lags a bit because people actually manually do this work, and there's a lot of work. But on the episode guide here, if you click on news and forums and episode guide, these are annotated ones where you can actually see stuff like timelines of what was covered. So if you should check here first if you're trying to catch up with older episodes, because these have a lot more information in them than just viewing it directly on the YouTube. But if you're trying to look at one that just got posted, they aren't quite in the episode archive yet. So. Would a memory mapped virtual file system be a BAS move them? I have no idea what that means. Sorry, I do not know. Oh, bad. Would be a bad move. Well, memory mapped virtual file systems have some problems. The first thing that there's a problem is you can't run on 32-bit. Because if you have more than 4 gigs of audio-visual data and you want to run on a 32-bit system, well, you can't memory map the file, right? So you'd have to memory map the file in chunks, and if you're memory mapping the file in chunks, you might as well just load it, right, with traditional loading code. So memory map virtual file system, I don't know. I mean, on 64-bit, memory mapping, I don't know if I like it. You don't have control over when the operating system is doing that paging, so I don't know. I don't love memory mapped files, to be honest with you. I like them for certain things. We use them in the recording. For certain things, they make sense when you actually have something that's basically memory backed by a file. But in this case, that's not exactly what we have because we never write to it even. So it's a little unnecessary, and you lose a little control of when the operating system goes to do the actual reads. Will Handmade go with a loading screen or streaming method resources? Streaming. So definitely not loading screen. Can you go over how streaming fits into the GWAR? Yeah, so basically what will happen here, and we'll see this in a second, but what will happen on the diagram is very much like what I've drawn here. We will be inside GWAR, right? And I talked about this way back when I talked about the platform layer at the very beginning. And if you remember, I talked about that we implemented like a debug load file, debug save file thing that we have in there for now, and that's what we'll be using to load assets just to start with. But when we go to actually do our streaming, what will happen is basically there will be a queue exposed. So when the Guar calls in, it's not passing one currently. It'll pass a queue in here that the game can write to that basically will allow a threaded resource loader in the background to load things for the game. So a queue will come in here and it'll do writes to that queue. That is how it will kind of come in on Guar. Game engines often run update and render prep in separate threads in order to exploit hardware parallelism. If you combine update and render, will that prevent you from doing this? No, and often that is not a very good way to split those two things, actually, because of the cache coherency problem I just mentioned. So if you imagine, I mean, it depends. In streaming scenarios, maybe it doesn't matter, so I shouldn't say it's... I overspoke. I wouldn't say it was bad. I'll simply say that it's not relevant in terms of performance. The reason why is because if I want to, right, if I have something where I've got a bunch of stuff that has to get updated, right, I can choose to split it either way. I can either say, like, you know, each one of these things has to get updated and rendered, right? So I've essentially got, you know, object 0, 1, 2, 3, whatever they are, particles, who cares, right? So I've got update and render. If I choose to do, when I choose to do my threading, I can do that in one of two ways. I can do it using one of these vertical lines here. Like, and you could almost imagine it's not update and render. You could imagine this was any number of tasks, right? You've got, you can think of it like a matrix. Let me just draw this out for you. I think it's pretty important to understand. So I'm gonna go ahead and draw it. Okay. So you got your code, right? And you wrote it single-threaded, so you just wrote it, you got it working, right? Now you want to think about it in terms of how do you get threading performance out of this code, right? So here are the like elements. So I have element 0, element 1, element 2, element 3, and these can be whatever they are, right? They're objects, they're particles, I don't care what. You then have steps. There's step 0, step 1, step 2, and so on, right? So all of these sorts of things, each one of these boxes has to happen. In single-threaded code, you can think of traversing the matrix like this, right? I start with element 0, I do step 0, I do step 1, I do step 2. I go to element 1, I do step 0, I do step 1, I do step 2, right? Whatever those steps are. And these steps, you know, maybe it's just update and render, so there's only 2. Maybe it's update, render, and like, you know, write to disk. I mean, I don't know. Who knows, right? Whatever it is, I've got 3 steps here. Update, you know, frobnicate, because that happens. Obviously, everyone frobnicates things once in a while, and then render. So I've got steps that can be split up, right? So one way is that zigzag pattern. That's the single-threaded way, and that's obviously the slowest way because you're not taking advantage of any of the cores of the processor. But sometimes that's the best way to do it because if you know you have lots of things, other things that could be going on at the same time, there may be no reason to write something multi-threaded. So obviously you always want to think about first whether there's even a reason in your particular game, given in your target platform profiles and stuff, whether you even need to. But this is single-threaded, right? That's how that looks. Then if you multi-thread the way you were suggesting, where you say you split them into 2 parts, that looks like this, right? The threads go in columns here, right? So one thread does the update, one thread does the frobnicate, one thread does the render, right? So there you go. That was the thing that you were suggesting. Well, I don't think that's a particularly compelling way to do it. One, because we know there's a dependency here, right? So now I have to have job control understand that this update has to happen before this frobnicate, which means that I can't even actually run them together like you were suggesting. They can't actually be parallelized because the updates have to happen before the frobnicates happen, and the renders have to happen before after the frobnicate. So job control is actually going to have to serialize these things to a large extent, which doesn't sound particularly good to me, right? So that's bad. The other thing that's bad is it pulls it into the cache multiple times. So whatever element 0's data was, any data that might have been shared between these two things now has to get pulled in by each thread. So it's going to get pulled in twice, right? Or 3 times, potentially. Furthermore, if update produces any residuals that Frobnicate needed, right? Like let's say it computed something that Frobnicate also would need to compute. Well, either it writes it out to element, which now burns a write because it would have just been on the stack, or it has to be recomputed in Frobnicate, which wastes a bunch of cycles, right? So I don't love, sometimes that's appropriate, but I don't really love doing it that way. What I would prefer to do is break it up this way, right? So basically, there's somebody doing one zigzag that way, and then somebody doing a zigzag this way, right? Basically, break it up by rows, right? Because this way, the dependency is inside the code still, and it looks exactly like the single-threaded code looked, right? But now you just break it up by which one is, by what group of elements it's actually working on. So, I don't know. So, personally, I tend to prefer writing it that way if you can. If for some reason you have to write it this way, well, okay. But I feel like a lot of times it's better to write it the other way. Since the human eye can only see at 70 frames per second, is it worth it to put in a max FPS allowed? Well, we will put in a max FPS, but not because of that reason. We'll be putting in a max FPS because at some point our floating point values will break down, and so we need to make sure that our time step it doesn't get any smaller than whatever that is. But I would point out that the human eye can actually see greater than 70 frames per second. It can see at least 90. So, I wouldn't go so far as to say that 70 frames per second would be a maximum anyway. But yeah. How are you going to handle VSync? Well, we already kind of do handle VSync in some sense, meaning that we have the code structured so that when we switch to D3D and OpenGL, it'll just kind of work because we're actually doing our own spin lock there, waiting for the mythical 60th of a second. But what we will do in the future is just actually call D3D or OpenGL, and it will do the VSync on the flip. So our code's already set up to handle it, so we won't really have to do much to make that work. Let's see. For avoiding cache misses when you separate update and rendering, can't you store the same types of components together in memory? So for example, you would loop through and update the physics components and then the render components for all entities. Well, no, because they're the same components, right? Whatever physics is creating, right? Physics is going to write, I'm going to do the physics code, right? I have to update the position, the velocity, right? At the very least, possibly some other things. The position and the velocity are probably needed by the renderer. The position at least is needed to know where to render the thing, right? So I need the position. Velocity is probably needed if I'm doing any kind of motion blur or other sorts of effects. I might need that as well. So they're not separate sets of data. They're the same set of data. Now there are some things that the physics will use that the rendering won't use. And so yes, that part you don't have to worry about because you're not polluting the cache with that. In the case where we're doing like this, but you are definitely wasting cache bandwidth reloading these things. So it's just not as efficient if you can make it work if you can do it this way instead. You said tasks. Does that mean async job system? I don't know if this game will actually need an async job system per se. I think this game is probably going to be scoped such that it doesn't require a full async job system. And the reason for that is because, of course, one of our target platforms, which is the Raspberry Pi, has one core, if I remember correctly. So we really can't go crazy with multi-core. We've got to kind of stick to something reasonable. So the things that will multi-thread are mostly going to be like the renderer and stuff that will then use GPU on other platforms and that sort of thing. And asset streaming, which is not really about threading so much as it's about overlapping disk I/O. So. Let's see, Panda Tipper, when will we see you actually creating the game? Well, we'll start programming the game tomorrow. So I'm not sure what you mean by creating the game. but starting programming the game tomorrow. But we're going to be doing rendering work as well, Interleave. So we'll, I mean, if you're talking about when will we actually be mostly working on just game code, it'll still be quite a while because we got to do rendering work interleaved with our game work at the moment because we haven't written any rendering code yet. Will we be making a physics engine during the series? Yes, but not, I mean, it depends what you mean by physics engine. We'll be making an engine that does the physical stuff that we need it to do for this game. But, you know, we're not trying to make Havoc or something like this. Since this is a 2D game, it wouldn't be 3D physics anyway. It's 2D physics. That makes sense. Is there any issue with posting a JS HTML5 port on my GitHub? So basically, the way that the code is still copyrighted until eventually we release it into the public domain, which I put a time limit on that. It has to be 2 years from when the game ships or earlier, basically. So you're not supposed to be posting Handmade Hero code to GitHub. If you're just trying to post a ported platform layer that you did, then be my guest, because, hey, you wrote that platform layer, right? And I don't have any interest in stopping you from posting it because other people can learn from it, and, you know, that's been great. So there's been a bunch of people who have posted platform layers. They all asked me for permission, and I said yes to all of them. I would basically say that posting platform layers is okay. Please send me a note and let me know where it is, because we probably will want to put it on the Handmade Hero site and point to it. But what I would like to avoid is posting the source code to the game anywhere. That's not allowed, primarily because that's like one of the benefits you get from pre-ordering. So that's like part of the product is the source code. So that is not supposed to get posted anywhere, if that makes sense. When things do get released into the public domain, I will make it very clear. So I will be announcing anytime I take a chunk of code and release it into the public domain, because I may release some code earlier into the public domain. I will, you know, make it very clear what that is, and the license.txt file in the distribution will change to reflect which files are allowed to be sort of done with what you will. All right, looks like we are done with questions. Right on time, too, 9:28. All right, thank you everyone for tuning in to Handmade Hero for our architecture discussion. Tomorrow we will start actually programming the game structure, so we'll kind of be like making some little things and kind of, you know, building the architecture by doing the same kind of process that I was encouraging for just writing the, you know, the basic game, the basic platform layer code, where you just kind of write the first thing that comes to mind when you're trying to build something, and then you kind of loft it up into an architecture as you go. We'll be taking that exact same approach, and as we go, I'll be constantly referring to the stuff that we talked about today in terms of reasons why I'm making certain decisions as we do the lofting. So I hope you will join me tomorrow. It is going to be at an odd time, and let me explain one thing really quickly to people since we're on holiday hours now. At any time, if you go to the news and forums link here, on the front page, the very front page, always has the schedule. So if you want to know what time it's going to be, you can kind of see basically what the times are. You'll notice this one is at 8 a.m. tomorrow. So we have a very early stream happening tomorrow morning. So be aware that tomorrow's stream, 8 a.m., which again is because of holiday hours. I've got events during this week that will be taking place at times that would have been normally where the stream would normally be. So they have to be moved a little bit. And then for the rest of the week, it will be at 10 a.m. So it's definitely going to be a lot of earlier times. Now, if you can't make those on Twitch, no problem. Everything gets updated immediately thereafter. So in fact, the stream should be uploaded to YouTube and watchable on YouTube even, not even on Twitch's replay, but on YouTube, by the time the normal 8 p.m. slot rolls around. So you should be able to watch it just as normal. It just, unfortunately, you won't be able to ask Q&A. But if you do have Q&A, you can always go to the code discussion thing here that we have, and you can put it in right there. Okay, so if you would like to work along at home with the source code, you could pre-order the game and you'll get a download link that allows you to download the source code. And if you just want to support the video series, we have a Patreon that you can subscribe to. I think that is absolutely everything that's on this page. Obviously, there's the Twitter feed, which I try to tweet whenever things are happening, and a live link to Twitch, but you must already know where that is because you are here. Thank you, everyone, for joining me. I'm kind of excited about tomorrow to start typing in some game code. I think it's going to be pretty fun. We will, I think we will probably make pretty good progress. It only took us 25 hours to do the prototyping layer, roughly. That's pretty good time. Like I said, that's not even a week worth of a full-time coder's time. So I'm interested to see how much progress we make on the game code. I'm interested to see how long it takes because I've never programmed live stream game code before, so I don't know what the time difference will be. But I think it'll probably go pretty well. But we will also be trying to take it slow so we can explain absolutely everything. Unlike the Win32 platform layer, where it's not really that important to understand how Windows works because it's just yet another platform into multiple platforms you have to ship on, and nobody ever understands all the complexities of Win32 anyway. We will certainly be spending more time on explaining stuff in the streams for the gameplay code, just because it's stuff that you can understand completely, and we will be writing all the source code for it ourselves. So I think that'll probably be pretty interesting too. So thank you very much for joining me, and I hope to see you all tomorrow bright and early at 8 a.m. But I suspect I may end up mostly seeing people from Europe who are already up at that hour. But either way, if I do see you, good. If not, I hope to catch you on the replay. And thank you very much for joining me.